Okay, so welcome to the last section in this chapter. This section is going to switch gears. It's going to talk about something called reciprocal functions, where the first three sections talked about absolute value functions. We're just going to do a brief introduction to what reciprocal functions are all about. Basically, if I was given the graph, if I was to give you the graph, y equals f of x, okay, its reciprocal would be 1 over f of x. The moment you move things to the denominator, though, you're going to be left with restrictions, okay? There's going to be possible restrictions. And these restrictions are, is when f of x is equal to 0, okay? Because you cannot divide by 0. So basically, this slide here, we're going to define what a reciprocal function is. Okay, if you're given some function f of x, its reciprocal is 1 over f of x, provided that f of x cannot be 0. At 0, you're going to get points. Okay, at 0, f of x is undefined. Undefined. Okay. So let me just show you what a reciprocal function looks like. It's a bit odd. Okay, so the example I'm here is going to be y equals x, and the reciprocal of that is 1 over x. Okay, on the graph below here, so in blue, the graph of y equals x is a straight line. Okay, in red we have y equals 1 over x. As you can see, it's already labeled. Why does it bend like this? What a strange graph. And it all comes down to these restrictions. These points are common, okay, and they so happen to be at 1 and negative 1. Okay. The reason for that is because at 1, when x is 1, the reciprocal is the same. Okay. These points right here are called invariant points. Invariant points. Okay, intersection. And they always occur at 1 and negative 1. And that's because the reciprocal of 1 is 1, the reciprocal of negative 1 is negative 1. Therefore, the reciprocal function and the function itself, f of x, will equal itself and therefore intersect. But what happens to this shape? What's up with the shape? Well, this happens because, for example, I'm going to draw a dotted line in green. This dotted line is the point, or the line x, not y, the line, let's draw this in, yeah, green. X equals 0, okay? That is a vertical asymptote. And what's a vertical asymptote? This is when the graph takes values that are undefined. In this case, it will be 0, because y equals 1 over 0 is undefined. So wherever x is 0, which is at the origin here, the graph will not be able to touch it. It will get infinitely close to it, but it will not touch it. Therefore, you get this shape right here. You get this shape where it's approaching the line, but it will never touch it. What happens here, though? Now, this is not because of an undefined operation. This is because of the nature of a reciprocal function. This is due to the nature of a reciprocal function. When the reciprocal function takes large values of x, let's say 1 over 2, and then say 1 over 3, 1 over 4, 1 over 5. Notice how x is growing. Okay, well, that was just terrible. That has to be rewritten. X is growing, but 1 over x is getting small. So as x grows larger, that means as you move along the axis this direction or in the opposite, okay, then you're going to get very, very small values that are going to approach 0, right? This is 0.5, and then you're going to get 0.33, and 0.25, and so on and so forth, and you're going to get very, very close to 0, but once again, you're not going to touch it. This is called a horizontal asymptote, okay? Horizontal asymptote, and that would be, in this case, y equals 0. Okay, the asymptotes don't have to be at 0, or for the vertical asymptote doesn't have to be at 0. It can shift left or right. In reciprocal functions, the horizontal asymptote will always be at 0. Okay, and this is because the degree of the denominator will always be greater than the degree of the numerator, which will result in this. Okay, so all you have to remember is that this will be at 0, but the vertical asymptote can change. So I went through an example, and the first way I graphed it is with the table of values. Okay, so let's do that. Let's go ahead and graph with the table of values and see what this gives us. So the first function we're going to look at is f of x equals negative x, and what a table of values will look like is the following. And there's a reason I'm doing this in different colors. So you're going to be able to see, and I apologize, we are working with the negative x. So here we go. The first step is to find the intercepts. This will give us a good reference point on the table of values. Here the intercepts are 0. Okay, and let's choose these points. So you're going to choose points that are symmetric about the intercepts. Okay, put the x-intercept to be specific. So from here, we're going to have, you gotta be kidding me, 1 second. Okay, from here we're going to just basically plug the points in and see what they give us. So this will give us -2, that's -1, that's 0, that's 1 and 2. Totally symmetric. And this is going to give us negative 0.5. This is going to give us -1, that's 0. This will give us 1 and 0.5. Okay. So from here, let's plot the blue graph first. That's the original graph. So here we have our intercepts at 0, then at -1 and 1 and 2 and 2. There's the graph. Okay, that's y equals -x. Then when you take a look at the reciprocal function, we get another point at 0. At -1 and 1, we get our invariant points. Like I said, they always happen -1 and 1, so they'll be the same. The next points are smaller. Okay, they are going down here, and this other one is going to be right around here. But this is impossible to graph unless you draw the asymptotes, and in this case the asymptotes will be, once again, at 0 and 0. Remember, take a look at this. When x is 0, it's undefined. Okay, and actually that's my mistake right here. This should say undefined. Undefined. Therefore, when you graph, you're going to be going through these points, and this is what it looks like. Okay, so you can kind of see how the vertical asymptotes kind of lead you to the answer. All you need are the invariant points, and then you can fill in the solution from that. So let's do another example. This time I'm gonna graph it in a different way, probably a more convenient way than the table of values. Sometimes the table of values can be a bit inconvenient. So for instance, in this question, we're doing f of x equals 3x minus 9. So here, what we're going to do is determine its reciprocal function, which in this case is going to be 1 over 3x minus 9. Determine the equation of the vertical asymptote, which means we're basically looking for when this is 0, which in this case would be when x is 3. Okay, that's the equation of the vertical asymptote, and now we're going to graph it. So to graph it this time, instead of, you can use a table of values, I should say, table of values. If you want. However, there's other methods. Okay, you could simply graph y equals f of x, find the invariant points, and then fill in the graph from there, which is what I'm going to do. I'm going to graph y equals f of x. I'm going to find the invariant points. Those are the points of intersection. And then plot the asymptotes. So here's a nice little step-by-step. And then I'm going to graph y equals 1 over f of x. Okay? So to do that, remember we're dealing with 3x minus 9. To graph this, it's y equals mx plus b. That's the form. So your slope here is 3. Your y-intercept is negative 9. So when you take a look at this graph down here, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the y-intercept. The slope is 3. So you go 1, 2, 3. That's your rise. That's your run. Anyway, 1, 2, 3. And you can plot as many points as you want. Once you're satisfied, you can plot this line. Now don't worry if most of your points are lower down on the axes, because all the action is going to happen at this x-axis, because that's where the horizontal asymptote always is. Okay, so that's where it always is. That's y equals 0. The vertical asymptote this time is at 3. 1, 2, 3. Kind of jumped ahead of our steps, but now we know what the axes. Now we know what the asymptotes are. So now all we need to know is the invariant points. Okay, the invariant points. There are a couple ways of doing this. Okay, one way of finding the invariant points would simply to set both graphs equal to each other and solve for x, which is a pretty easy way of doing it, because remember, intersection means they have to equal each other. So what I mean by that is you could actually simply solve this, okay, equation, and this is going to give you, okay, dot dot dot, that will give you the points of intersection. We can kind of have been doing this because we can have an easier way, because they always will happen at 1 and negative 1. Okay, that is, okay, when f of x is plus or minus 1, which is y is plus or minus 1. And here's the deal, you can actually do this for either graph. You don't have to do it for both. Okay, in the example before here, I did it for, I solved for both, but then I gave you a little note that you only need to calculate the invariant points for one of them, f of x, because remember, it's intersection. Notice how in this graph, this is the previous example, these are the invariant points. See how they happen at 1 and negative 1. You go back a bit, take a look at the next ones. Happens at 1 and negative 1. Next example, there's 1, there's negative 1 invariant points. So that's always where they'll happen. That's where they'll be. So when we calculate them, we should just do it for f of x. 3x minus 9 equals 1. Therefore, 3x equals 10. X equals 10 over 3. Okay, that's one invariant point. And then we have 3x minus 9 equals negative 1. So we're going to have 3x equals 8 in this case. So x is going to equal 8 over 3. Okay. Let's convert this to a decimal. 3.3 and 8 divided by 3 is 2.7. Okay. So let's just plot those points. And maybe I'll just draw the points for this first one right here. Hey, for this first one right here, we're going to be left with 3.3 and 1. And this one right here, we're going to be left with 2.7 and negative 1. So those are the points you should plot. So when we plot those, 3.3, so that's 1, 2, 3, 0.3, and negative 1. There it is right there. Remember, they have to be on this graph. And then the next ones will be at 2.7 and negative 1. I'm sorry. 2.7. That's where that first one is. I'm afraid of trying to erase that without erasing everything here. Let's see if I can there we go. This point right here is 3.3 and positive 1, which is right here. Right there. So now that you have these, you can kind of fill in the graph. You have a very good idea of what this graph is going to look like. You just need to know when they turn. Okay, and that's it. I think it's a much easier method of using a table of values if your goal is just to sketch. Okay, just to sketch. So let's move on to another example. This time we're going to have a quadratic function, and I'm just going to give you a little foreshadow. Hopefully you've read through this before. The procedure is the exact same, except you're going to have two vertical asymptotes, and the graph is going to look a bit different. Look in blue. That's basically what the original function looks like. The reciprocal function, again, take a look at these vertical asymptotes right here. Okay, that kind of fills in the picture, right? And you also have a horizontal asymptote going across, okay, the center. What else could the solution be, really? Right? What else could it be once you have these points? The question will fill in itself. Okay, so the name of the game is to find the invariant points, find the vertical asymptotes, and graph the original function. So that's what we'll do in this next question here. Consider f of x equals x squared plus x minus 6. The reciprocal of it is, of course, y equals 1 over x squared plus x minus 6. For b, state the non-permissible values of x in the equations of the vertical asymptotes. Well, we're solving this. Right, that's what we're solving. In this case, it's 3 and 2, and it's plus and minus. So x equals negative 3, x equals positive 2. These are the vertical asymptotes. Okay. For part C, the x-intercepts and the y-intercept of the reciprocal function. Okay, that's an interesting piece of information that we could make use of. You actually will let y equal 0. And when you do that, what we're going to be left with is 0 equals 1 over x squared plus x minus 6, which basically means 0 equals 1, which can't happen. So of course there are no x-intercepts. Okay, which makes sense because there's a horizontal asymptote at that point. The y-intercept is possible. Okay, we're going to let x equals 0, and that immediately gives you a solution of 1 over negative 1 over 6, okay, which is where the y-intercept will be. Okay, so now we have to graph this guy. So we have x squared plus x minus 6. So we have y equals x squared plus x minus 6. Right. And we have our x-intercepts at 3 and negative 2, correct? Negative 3 and 2. Negative 3 and 2. So when we draw this graph, when we draw the graph, we are left with 1, 2, 3, 1, 2. Okay, there's our how do you say, x-intercepts. Now, if you want to find the vertex, okay, if you want to find the vertex, so you can see if I go back this point right here, you're going to be forced to complete the square of this equation, which very quickly, this will give us the following. We're going to have y equals x squared plus x minus 6. This is going to equal x squared plus x plus 1 over 4 minus 1 over 4 minus 6. Y is going to equal x plus 1 over 2 squared, and negative 1 over 4 minus 6 is equal to negative 25 over 4. So your vertex in this case is negative 1 over 2 and negative 25 over 4, which is negative 0.5 and negative 6.25. So right away, let's graph this. Okay, negative 0.5, 1, 2, 3, 4, 5, 6. And here we are. Okay, so now that we're left with that, now all we have to do is plot the vertical asymptotes, which occur right at the x-intercepts, which we get the following. Okay, horizontal asymptote at y equals 0. So if x equals 2, x equals negative 3, right, from before, from previous. Now from here, we need to plot the invariant points. Okay, you can kind of see what the solution is going to look like. We also can plot a few other points on this graph. We know that the y-intercept is at negative 1 over 6, okay, of the reciprocal function. So that's negative 0. That's a really negative 1 over 6. That's the y-intercept. Really small. Basically right here. And you should expect 4 different invariant points here, right? Something in quadrant 2, something in quadrant 3, quadrant 4, and quadrant 1. Okay, 1 to 4. There should be an invariant point for each one here. So to do that, let's do our regular x squared plus x minus 6 is going to equal 1, and an x squared plus x minus 6 is going to equal negative 1. Okay. To save some time, let me just give you, when you solve these, the solution. Okay, so those are the solutions. You have to go through the quadratic formula to get these solutions. It'll take a bit of time, but it's nothing special. So now we go through there. Let's plot these points very quickly. 2.2 is just over here, and remember your y-intercept is, your y value is 1, so we're really looking at here is one invariant point, and the next one at negative 3.2, I'm looking at this one right here, negative 3.2 for x, 1, 2, 3, and we're at 1, so we're really looking right there, just as you expect. And 1.8, x equals 1.8, so roughly here, except we're at negative 1, so we really are up here. And negative 2.8 and 1, so we're roughly here. So really what this will look like is what you see in green. I'm trying to not screw up too much. Okay, they're not square lines, they're rounded, but that's basically what it'll come out to be. Okay, so that's how you graph them. It's very long questions, but hopefully that makes sense. The last type of question is if we're given a graph, okay, if you're given a reciprocal function, can you graph the original function? And can you determine what the original function is? Okay, so the first step will be to basically find 2 points. 2 points that would be in the original function. And in these questions, I'm only going to give you ones where they'll be linear. So maybe I'll say that. These will be linear. Okay, I won't give you any quadratic functions. Okay, so let's just do an example. So here's the reciprocal function we're dealing with. Okay, we don't know what the original is. We don't know what the reciprocal is. But what we do know is we know this vertical asymptote is at x equals -1. Okay. Okay, that's going to be important. Okay, x equals -1. You can see that's going to be a point. That's going to be a point on the original function. Will be -1 and 0. Okay, that is an x-intercept of f of x. Okay. Now you just need to find the invariant points, or you could find a different point. Notice how I actually give you 1 point here. I give you this point right here. -2 and -1 over 4. Okay, -2 and -1 over 4. Since we're talking about a reciprocal function, -2 and -1 over 4 really will be -2 and -4. Remember, because y will flip. The y value will invert. Okay, always the y value will invert. And so what you're going to be left with is -2 and 4, which is down here. Now that you have 2 points, you can go ahead and connect the dots. Okay, that's for part A. Part B is determine what this line is. Okay, which is not too bad because you have 2 points, so you can very simply find the slope. Okay, the slope will be y2 minus y1 over x2 minus x1, which in this case is -4 minus 0 over -2 minus -1, which is -4 over -1, which is 4. Okay, so the slope is 4. So far we have y equals 4x. Now, how do we find the y-intercept? Well, we know y equals mx plus b. We're going to solve for b. We're going to choose 1 point, let's say -1 and 0. Placing it in, we know the slope is 4, -1, and solve for b. Therefore, b appears to be -4. B appears to be 4. Okay, which makes sense because my line is atrocious when you think about it. If I was to redraw this, it really does go through 4. So here, that is the original function. So sorry for the very long video. Hopefully you kind of skip through some stuff, or if you watch the whole thing, hopefully this makes sense to you. Once you're finished 7.4, do these practice problems, work on the assignment, and then move on to the exam.